So here we have our largest standard square on our regular grid. Of course, you know that this is an enlargement of it, but as we are about to draw the graph, then you'll see a better representation of it. We're just enlarging it at the moment for the purpose of explaining the scale and also to get us familiar with the sizes of the different standard squares on your regular grid. We will be solving a problem that requires understanding and interpreting the scale of a graph. If we are going to do that, then we must be familiar with the squares on the graph. We will begin with the knowledge of the actual sizes of the different size squares on a regular grid. So on your regular grid, we have some standard squares, and we need to be aware of the size of each of those. Now the first and the largest of the standard size squares is your 2 centimeter square. So the largest of the standard squares on the grid is your 2 centimeter square. It is a square of which each side is 2 centimeter in length. Then the other one, which is the one smaller than that, the squares next in size have sides equal to half of the side of the larger squares. So the next one is side equal to half of the side of the larger square. They are of side equal to 1 centimeter in length. So the first is your 2 centimeter squares. Then the second is your 1 centimeter square. But of course we have the little teeny weeny squares. What do we know about those little teeny itty beeny teeny weeny squares? Notice that in 1 centimeter we have 5 of them. The sides of 5 teeny weeny squares are in each centimeter, and of course each centimeter is equal to 10 millimeters. So here we have 1 centimeter, and in that 1 centimeter we have 5 little squares in that 1 centimeter. That 1 centimeter is also equal to 10 millimeters. So in that 10 millimeters we have 5 little squares. What does that mean? That means that the size of each of those little squares is 2 millimeters in length. So the side, each side of those little squares is 2 millimeters in length. So we have your 2 millimeter squares, we have your 1 centimeter square, and we have your 2 centimeter square. Those are the sizes of all 3 standard size squares on your regular grid. Therefore, the side of each of the very small squares is 2 millimeters. So there is your grid. Of course, you can see that the boldest lines are your 2 centimeter squares. The boldest lines. And then, of course, you know that we have your 1 centimeter square following, and so on. And it is a beautiful grid. I designed it myself. So let us take a brief look at the scales on the axes. As you can see it is very, very clear. It is blatant. It cannot be clearer. So what we have there, as you can see, not just right here, but you can see that for each 2 centimeters length, it goes up by 10. So 2 centimeters, 10 units. 2 centimeters, 10 units, because it goes up by 10 each time. So 10, 20, 30, 40, going up by 10 each time for each block of 2 centimeters. So what do we know about that? The 2 centimeter squares, that's what we are looking at, its side is 10 units. So from here, which is 2 centimeters, that is represented by 10 units. Anything to follow? 10 little squares for those 10 units. Now we can do a little calculation and we can see it. That is the beauty about graphs. The beauty about graphs is that it is visible, it is practical, it is obvious. Now we have 2 centimeters. First of all, we have 5 little squares in each centimeter. So we'll have 10 little squares for 2 centimeters. But it so happens that in this particular case, we have 2 centimeters to 10 units. So if we check, we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 little squares in 2 centimeters and 2 centimeters to 10 units. 10 units, 10 little squares, each little square is 1 unit. So that's obvious. So 10 little squares for those 10 units. 10 units divided by 10, that is equal to 1 unit. Each little square is 1 unit. It is true on the horizontal axis, it is the same. The scale is the same on the horizontal axis, so we just say that the scale is the same on both axes. Our concern at the moment is half of a unit. Not only its calculation on how it is related to the graph with the presentation, but can we actually represent half of a unit on the grid? Can we represent half of a unit on the grid? So our concern is the half unit in the table of the horizontal axis. And we'll see why in a minute, because we're not just looking at this setup just for the sake of explaining the scale and so on, which is, if it's just for that purpose, it is going to be for a good purpose. But we are going to apply this in constructing a histogram, which means that we have additional practical application. 1 little square is 1 unit. Therefore, half of a unit is half of a little square. We have a definite calculation for it. Let's see if it may be represented on the graph. So we are going to put that on the graph, the half of a unit. You know that half of a unit is half of a little square. Of course, we can see half of a little square. We can see that. So it means that it should be able to be depicted on the grid. So on the grid, draw a histogram to represent the distribution. Now we had a table with everything inside there. Limits, cumulative frequency, frequency, upper and lower class boundaries. Now, only one axis is labeled, and the labeled axis is the frequency axis, as we have it right there. On a histogram, frequency is plotted against the measured quantity, and the measured quantity is volume in this case. The label of the horizontal axis must therefore be volume. So remember, we are looking at the volume of petrol in the tanks of vehicles, and of course that will be the measured quantity of the horizontal axis. So the measured quantity of the horizontal axis will be volume. With frequency on the vertical axis, the class boundaries, which are related to the measured quantities, are the values used on the horizontal axis. So with frequency on the vertical axis, the class boundaries are the values used on the horizontal axis. And of course, you know that the class limits, the class boundaries, those are related to the measured quantity, which is the volume of petrol. The boundaries will be the horizontal margins and the frequency will represent the height of each bar. Also, remember that the bars are joined. Consecutive bars of a histogram must be joined. And what do we mean that they must be joined? Where one bar ends is where the other begins. So that is what we have for your histogram. Joined bars, and that is representing what? Continuous data. So there we have it. If we are going to construct a histogram, we must use the frequencies, and those are in relation to the lower and upper class boundaries. And of course, the lower class boundaries are actually values. They are actually values of the volume of petrol. So those measures will be on the horizontal axis. For example, we have 10.5. We have 20.5. Where will we find 10.5 and 20.5? They are in relation to the volume of petrol. Therefore, they will be located on the horizontal axis. So 10.5 will be right here. 20.5 will be right here. How do I know? Because we have 10 units and we have 10 little squares. We have 10 units and we have 10 little squares. Each little square will be 1 unit. So half of a unit must be half of a little square. And that is why I am pointing to halfway through the 11th square, the one after the 10th square, and so on. So let us go straight ahead. So first of all, our first bar goes from 10.5 to 20.5, and its height is 24. So it should go up to 20. 1, 2, 3, 4. Since each little square is 1 unit. 1, 2, 3, 4, right there. So that's the height. So the first bar begins at 10.5, ends at 20.5, and its height is 24. We have it right there. What will happen next? The second bar begins at 20.5, ends at 30.5, and its height is 35, as we have it right here. So it's going to begin where the other one ends, 20.5, 20.5. So it will begin there where the other one ends, and its height will be 35. That one, the third bar, will begin at 30.5, end at 40.5, and its height will be 42. 40, and then 1, 2. There it is. The third bar begins at 30.5, ends at 40.5, and its height is 42. So where one ends is where the other begins, and that is how we show continuity, because we are representing continuous data right there. The fourth bar begins at 40.5, ends at 50.5, and its height is 28. And of course, we always see the half a unit right there, half of a little square. It is always a half over. Finally, your fifth bar begins at 50.5, ends at 60.5, and its height is 21. 20 and 1. So 20 and then 1 more right there. Great. So that is the construction of your histogram. Do not forget that when you are constructing histogram, you cannot use class limits. You have to use class boundaries. Why? Because the limits are not in such a way that where one ends is where the next one begins. So there's going to be a gap between the bars. But the glass boundaries where one ends is where the next one begins. There is no gap. The bars are joined, and we have continuity depicted in that way. A histogram is used to represent continuous data. Continuity is depicted by the joined adjacent bars. For a cumulative frequency curve, which also depicts continuity, continuity is depicted by the unbroken curve. And that's what we have for a cumulative frequency curve. It is an unbroken curve. And for the histogram, the bars are joined. Teachers and instructors, get unlimited access to teaching aids for your virtual classrooms at richardjamesmathematicsresources.com. Also, this is the best place for the hearing impaired to master mathematics as long as you are literate.